We got 30 folks in here now. Rachel and Virginia, and Ty, how are y'all feeling? Do you want to go ahead and get rolling or wait a couple more minutes? Virginia seems like she's ready. Okay, cool. Rachel's got a thumbs up. Ty, and you're our lead instructor here this morning. How are you feeling, my friend?
Feeling good, thank you. Let's see, let me send out a link real quick to the web page that we're going to refer to. So this is on the pre-hackathon training sessions, and I will share my screen.
We need a step ladder.
All right. So you can go to this is just a website that scrolls through and has all the stuff we're going to talk about. So you can go to this yourself, and that way you can make it really big and easy to see and walk through. My discovery environment is broken this morning. So if I need to do any code with you, I'll bring in my little R Studio and show you something live while we're working on that in the background. But I don't think we need to do any of that because most of it is us just trying to get you to change the way you're thinking about this process a little bit. Let me change my with the viewer over here. Okay, so just try to make it so I can see as many people as possible. Good. Most people have their cameras off, understandably. It's early in the morning. Okay, so what we're going to talk about is sort of how to get yourself set up for doing analyses. So in the big narrative arc of what we've been talking about so far, we have shown you how to get into the discovery environment. Now with that discovery environment, which is your big computer, we want to learn how to get a bunch of data and bring it in, set that up in a way that's convenient for analysis, and then you can do your analysis. And so hopefully you, when we get to the hackathon, have a good grasp of all three of those steps and can easily link them together and start doing really cool stuff. Now, my job is to sort of give you a new way of thinking about moving data around. And, you know, as a PhD, we sort of have to start all of our lessons with some pontification about how it philosophically matters. So that's what you're getting now is that I need you to think differently about your data. And that's a hard thing to do, especially for people who have been working with data for a really long time at a really high level. But the way most of us were trained to think about data was something like a sculptor. Like you bring in this huge chunk of data, then you chip away at all of the things that aren't what you want, and you're left with this beautiful sculpture that is the thing that you want. And that involves getting that rock to you. And that is big and expensive and limits how much sculpting you can do. And the big data came around. It was originally defined as data that was too big to fit on a single machine. And so just that pure definition means that none of the methods that existed worked anymore. And that's why big data became a buzzword, is because we now needed all of these new techniques to be able to deal with data that was distributed across multiple machines that was too big to fit in one place. And so when you're thinking about analyzing data, I need you to now switch over to that multi-machine thinking. You just think there's no way I can do this in one machine. So you can't just build stuff from scratch like you would a house or a sculpture. You need to think of, how do I, instead of bringing all of the stuff to me, how do I just patch into all these streams of information? So if you think about those old operator boards that they used to have in the White House, where sort of operators had to sit and plug the phone line into a bunch of different places, right? There's just information trying to come in through every portal on that wall. And the president's sitting there just patching into which person are they talking to here or there. And, oh, I love the phone emoji. Thanks, Nate. So that's the thing we're going to really try to get to right now, is thinking differently about our data, thinking differently about how data should flow in and out of our analyses, and think differently about how we're going to organize those data. Okay. Um, excuse me, I had a little bit of a cough, so I'll try to not blow out your speakers. So let's give ourselves a little analogy to grasp onto so we can start to think about these tools and think about the way to conceptualize this. One of my favorite photographers is David Yarrow, and he loves to engage in this debate on whether you make or you take photographs. And what I love about this debate is that, particularly nature photographers often think like, I'm going to go and find the perfect spot, and I'm going to find the perfect moment, and I'm going to find the perfect angle. And then when that thing happens in front of me, I'm going to take the picture. But as you look at this picture right in front of you, there's no way this would happen naturally, right? That is a wild animal. And David Yarrow in particular is known for, normally you would take pictures of animals through a long telephoto lens, and that loses a lot of the detail and the richness and sort of the panic that you get from being close to something. And so instead, he puts himself in these metal cages and gets a really short lens and gets really close to these things, so you get the intensity. But every single thing about this is staged. And so what happened here is David Yarrow in his head visualized the scene and then went and figured out a way to create it. And that is what we need to do. When we are making, quote unquote, making a data cube, I want you to get, somebody posted some more images in the Slack, in the chat. So, oh, nice. Good gifts. Well, okay. So the idea here when you're thinking about data is you're creating this picture. That data cube you're making is this layered image. And you have to go out and figure out the stuff that comes into that and makes it creative. This one is another David Yarrow one that's absolutely amazing, right? It's just buffalo, but this is a made image. It feels taken, but to get those things charging right at you and get yourself placed right in the path of them charging with the short lensed camera, he's like in a protective machine right now to keep him from getting trampled from those buffalo. All right, so we're going to talk about the technology of capturing this with our other super favorite photographer, Ansel Adams. If you went into a house in the 90s, you definitely saw an Ansel Adams picture on the wall. And he was amazing, but this is how he had to take pictures, right? He drove this car around and he set up this huge machine on top of the car. And first he would have to say, what do I want to capture? And so he'd have to aim his camera at the scene, at the landscape. And then he'd have to say, how do I want to capture it? And for that, it was like, take a piece of glass, pour chemicals that are reactive to red, let them dry. Pour chemicals that are reactive to blue, let them dry. Pour chemicals that are reactive to something else, let them dry, to make your own film. So he's literally having to envision what the end product is going to look like when he's pouring chemicals onto a sheet of glass before he even opens up the frame. So when we are searching through data in the cloud, here's the scene I want you to have, right? The landscape, this is the unlimited landscape of data that you could go and retrieve from the cloud on anything that you could possibly imagine. You just have to point your camera at it. But then that information started to flow towards you, right? The light's hitting those trees and those mountaintops and everything, and it's coming at you. You now need to set up your camera to capture how much you want, the mood you want. You need to modify those data, and ultimately you're trying to get them imprinted on this piece of film. Our analogy here is that that final piece of film is our data cube. That data cube that you're building is an expression of what you want to say with data. It's an expression of the questions you want to ask with data. It's an expression of sort of the style in which you want to do those things. And so you have to think about this whole system when we're thinking about moving data in and out of our analyses on the cloud. Okay, so here we are with all of the packages that I have loaded that you don't need to worry about. But we're going to switch analogies real quick. We're going to bounce back and forth between these two analogies, but this is to get us a little more specific. So right now we would be thinking about the light through the lens in the old analogy, sort of how much light do you let in or do you let out? But when we think about moving data in the cloud, we have three really big problems that we want to solve right off the bat. So I'm switching analogies just to talk real quick about the three big problems we want to solve. First is called the rat through the snake problem. So here, could I take a quick poll in the chat for what people think is stuck in this snake? So I have cell phone, phone, jewelry box, cell phone, a keyboard. Ooh, that'd be a really tiny keyboard, but I like it. It's a mouse trap. So there was a mouse stuck in the mouse trap and it ate the mouse and the mouse trap. Yeah. If you remember the lawsuit between Samsung and Apple, this would have to have curved edges, I think, in order for it to be a cell phone. But yeah, here is an example of, I mean, there's a natural problem that snakes have of like how big of a thing that can they eat and get it through their system. But here, when you combine two data sets, a snake and a mouse and a mouse trap, you now have a really big problem getting those things through. Now, what is the cheapest, easiest fix we can give you for fixing this rat through the snake problem? Is a bigger computer. Okay, and so this is why we sent you to the discovery environment. The discovery environment lets you go bigger. It just lets you be a bigger snake, so that rat just doesn't feel as big. Okay, but as you can imagine, we're going to move to problem number 2. That only fixes some of the problems because we now move to the antelope through the python problem. So you have scaled up to be a much bigger snake and your appetite gets much bigger. And now all of a sudden you've still gone way, way bigger and you've eaten something that's too big for you. And now you have an antelope stuck inside of you. So how do we fix this one? This one is to mount data. So if we fix the first problem by giving ourselves a really big snake. But once the snake is really big, now we need to figure out some ways to pre-digest our food. We need to break up that food. We need to find a way to feed the food to us in smaller, more remote bits. Once we get those, we move on to the really high-class problem of trying to drink from a fire hose, right? You have calibrated the speed and size of input so the data can come at you really fast. You've calibrated your computer to be as big as possible so you have room to receive those data. But now those data are going to be flowing at you so quickly that it's going to be impossible to make good inference from those data. You just like can't run new random forest models every day or something to help you keep track of that. You now have this really, really big analytics problem for keeping up with that speed of input. So we're going to go through some solutions for all 3 of those problems, okay? So we already know the solution to problem 1. Get on the discovery environment, get a bigger computer. Number 2 is the mounting. We're going to talk about that right off the bat. And then we're going to move on to how to use AI and ML. And the second half of this lesson, not me, but the next instructor is going to talk about sort of how to use AI and ML to sort of help you keep up with this deluge of data that might be coming at you. Okay, so mounting data. Why do I say mounting instead of downloading? Well, we're plugging into that wall. So that we have that operator wall. It has unlimited amounts of data that we could plug into. And we say, bing, I want these particular data. Now let's go look at what we're going to find. Okay, these are just data on the web. This is a website called HydroSheds. This is a large repository of river-specific data. And we're going to go through one of the pages that just shows you all of the different data that are in this website. We're going to do that in a few minutes. But first, let's just talk about this one little element of mounting data before we get into the specifics of a bunch of types of data. Okay. And one of these types of data is called void-filled DEM. This is a special type of DEM where somebody has gone through the effort of filling in all of the little gaps. And specifically, this is a hydrologic website. And so they're really interested in water flowing down. So these are all the places in your raster where water might artificially get stuck because there's just a void in data, but the DEM is going to read it as a low spot in the terrain or something. And so you've had actual real, nice professional scientists go through and correct this in a highly professional way. Now, when you look at the data types here, they have a really high resolution one, 3 seconds. and they have a slightly lower resolution one and a slightly lower resolution one. They don't allow remote downloads for the highest of resolution. So if your question requires going to the highest of resolutions, the 3-second, then you're going to have to do the old way of downloading the data and importing it like you would expect. But if you can deal with 15-second data, this is geographic seconds, not time seconds, then those allow mounting, and that allows us to utilize this technology that I'm about to show you. Okay, so in here, let me make this a little bigger. This is, again, our code. And this right here is the address that I would have found on this website. So here, if I just go here and I say 15-second for North America, North and Central America right here, I left click and copy link, bing. So this is just like any generic link that you find on the internet where you want to download the thing. You're just getting the copy link. So I'm showing you a specific example, but this is very generic, right? I have just put that link in there. Now that link tells me a couple things. One, it tells me that this is a zipped file. So a lot of you that have downloaded files would be familiar with a zipped file. You have to download this thing and unzip it. And so, and then inside that zip file is going to be a TIFF file that we want to download. And so I have just put all three of those, I've put those, sorry, I haven't talked about the first one yet. I put those two things in a string. So glue here is going to pretend like they were continuous and I don't have them separated by a comma. I did that just so I could show you the three parts. Okay, so we have the link that I downloaded, or the link that connects to the download. And this could be any link you find anywhere on the internet. Here is the folder that you would find inside of that, or a generic version of that. Sometimes you have to download one of these zip files and open it to know what this file path structure is to fill this in. But that lets you just set it up so you never have to download anymore. And then here is the magic sauce, okay? VSI is GDAL's virtual file system. And it allows us to, instead of downloading this, to just plug into them. This is that plug. So why do I have two commands here? Well, VSI curl, this is the just read things on the internet. So if this wasn't zipped, and it was just a file that was available, I could just use VSI curl. And you'll see some examples of that later when I go through specific data. They're just open, they're not locked, they're not zipped. You just go and VSI curl and you just have plugged into them. And it's as if they're in your computer. This one, because it's zipped, I have to add VSI zip, which all it lets us do is peek inside that zipped folder. So we don't have to unzip anything. We're just peeking inside, still in the server, in the cloud. We're not bringing any of this into our machine. And then I have added, this is a piping function. So after I have glued together this address of the VSI zip, VSI curl, the address to download, and where I want it to go inside, I add this, which says, okay, and convert it to a raster. And I do that. So this is for a DEM at 15 seconds for all of North America. Here it takes 7 seconds, and I have a raster. So for those of you who have in the past downloaded, it can often take 7 seconds to unzip the folder that you've downloaded. It can, right? It could take an hour or two to download. Tyler asked, how do we know and find out which are accessible by GDAL? And I'm going to go over that a little bit. Usually you can assume that they are, and you try it. And if it doesn't work, it pops up with this warning that says this website does not allow remote download or remote access. And so it's like it's sort of a lock that people can put on stuff that you can't necessarily tell ahead of time. But when you ping the website, it'll just send you that message saying essentially somebody's locked this and won't let you. And that is because it's costing them money. I'm going to show you further down, we can do all of our analyses on their side before they give us any of this information. So we can do really complicated, all kinds of complicated functions, operations on these data, and the server has to do that. And then they give you just the end result. And if you do really big computations, that can cost them a lot of money. And so in things like the Hydro sheds, they're just turning off the highest resolution ones because it was probably costing them too much money to service those data for everybody. But I'll show you some more of those examples. Okay, so we pulled those data in 7 seconds. Now I want to show you that we can easily just, let me see if this is done. It's doing a final render with one. This function name is incorrect, but there's, as soon as this finished rendering, we'll just refresh this page and those will be fixed. Okay, so here is another example of past behavior. You might go, I'm going to download a DEM and I'm going to download a slope layer and I'm going to download an aspect layer. Instead here, I just grab those, I pull in the one DEM, which I haven't even pulled to my machine. I just plugged into, so I never have to download it. I'm just reading it directly from the server, but then I can take that and I can calculate the slope from that memory, and I can calculate the aspect directly from those memories. Do zipped TIFFs incur, the question is, do tip zips incur a performance penalty in the case of, I'm guessing, can you be a little more specific? Because I was talking about other things. Are you saying in the remote, this should be faster? But I need you to, Ian, if you could clarify your question a tiny bit, in which case you mean.
Yeah, sorry about that. What I was curious about was why HydroSheds had decided to mount zipped files there instead of just having TIFFs be available as cogs on in an uncompressed format. That was a little bit of an unusual choice, and I wasn't sure what was driving it.
Totally. I have no idea. My guess is it's something just in their mass production system. You know, they just do it because it's easy, but I don't know. But the nice thing is if you use the VSI TIFF function, it's just peeking inside of there and it can move things easily in and out and doesn't get any penalty for unzipping them per se. Should be just as fast.
Thanks. Sorry to break up the flow.
Ty,
no, please, not breaking up the flow. Good to ask questions. Go ahead, Elsa. Sorry.
I just wanted to point out Tyler's question as well, like how do you go about finding these data sets that are available in the VSI?
Yeah, give me it's down like another 3 steps in the presentation.
Cool.
Yeah. Okay. So for those of you who do a lot of geography, these will feel like just normal steps. I just wanted to throw them in here for people who, well, we need the information for later in the code, but I also wanted to just highlight it for people who don't do this all the time. Geographic data are projected in a particular way, and this is because you can never do a perfect translation between a spherical planet and a flat representation. And those different transformations have different codes. This one, 4326, is a really, really standard code. Probably most of the time, this is what people are going to ask for a request in. But they sometimes will return data in a different projection. So when we go, and this is coming up, I'm getting ahead of myself a little bit, but when we make a call for the data, we are going to do it using a spatial object. And that spatial object usually needs to be in this projection. And so we often are going to come up with 2 projections of our area of interest, one to compare the pre stuff and one to compare with the stuff we received. The question about what language this is in R, and all of these things work in Python nicely. Also, the code obviously is a little different, but these systems are meant to be agnostic to the particular coding language you're using at the end. Okay, so I've transformed into 2 different projections that I'm going to see later. The question is, do I have a Python version 2? I don't yet. We're trying to get that developed. I don't know if we'll have it done by the hackathon, but we'll certainly have it done really soon. But a lot of this code, because it's so specific, if you take this code and put it into ChatGPT and ask for a Python translation, it'll give you a fully working Python translation of the thing, because you're giving it really specific code to start with. So that would be my first step. And we'll try to get stuff written up for you. But if you need stuff right now, just take this and copy and paste it into chat and ask for a Python translation. Okay, here we're just generally talking about area of interest. So the specific version of this system that I'm talking about today is the one that was sort of designed for spatial analyses specifically. And so the thought there is, because it's a spatial question, you're going to have an area of interest, and that is essentially going to be your searching query. So you're going to ask the system to send you data, and one of the pieces of information that it's going to want is sort of what is the geographic limits, extent of that you want. And so right here, when I'm asking for bounding boxes, right? So first I have, this is the name of that DEM that I already pulled in. I then transformed it into 2 different things. And then I said, what is the bounding box around that? And that bounding box, I can then use as my request. Sort of, I say, here's the extent that I want to search. This one that thing is all of CONUS. So it's all of North America even, which is really big. And I made that request and it returned like 110 gigabytes of information, which was too big for almost everybody's computer. So instead I did one with just Boulder County. So in the discovery environment, if you've made your discovery environment big enough, you could start doing really big stuff. Again, this is how big do you want your snake to be? But right here, you're feeding your snake a very, very big rat. And here it's a much, much smaller rat. And so just for demonstration, I wanted to break out and do a much smaller rat so that we can get through this thing a little bit better. So get bounding box. This is a function through OpenStreetMap. I will show you a whole page that we have to aid you through getting OpenStreetMap data. And it's really easy. So right here, I've just given it Boulder County. Boulder, Colorado gives you the whole county. And I've asked for it as a polygon, and it just gives me a straight polygon. And then I can transform it into the 2 projections I need and get the bounding box of those new projections. I just need those values to make queries. Here is, sorry, these should be next to each other, but this extent, I essentially just did the same thing for the United States. I asked for a bounding box or a polygon of the United States, and then cropped it down to the same size as that DEM. Okay, now we're to the good stuff. Okay, so stack. So the answer. Okay, I have a question about, is there an easy way to keep track of memory usage and file size while working on the virtual machine? That's a really good question, Kelly, and I don't. Yes, it's on the dashboard, sort of in your discovery environment. I'm not going to go to it right now, but on the front page of your discovery environment, you get a usage. One of the bars on the left is like performance. So you don't do it from within the discovery environment necessarily. You'd have to open up the second window and go to your opening dashboard in the discovery environment, and it will tell you how much RAM, how many resources you're using, I think. But we should make that easier to use, especially with big data sets, because they can catch you by surprise. Because on my laptop, I have to open my activity monitor and just watch the RAM go, up and up and up and up and up as those things come in, because it doesn't even indicate it really well inside the code. So really good question. I wish I had a better answer for you. I can only give you that sort of answer. Okay, Stack, this is the spatial temporal asset catalog. So this is essentially supposed to be a Dewey Decimal System for spatial data sets. And it's not as good as a Dewey Decimal System because there's a lot more chaos in all of the data sets, but it's really good, and it at least has a system. So first, you are going to go to what's called a stack catalog. Here is just one stack catalog, element 84. Element 84 is a particularly nice, it's all these data are physically on AWS, which makes them cloud-based and fast. They're focused on Earth, their Earth data sciences websites. There is a V0 that has more low-level data and V1 that has slightly higher level data. And we can go onto there and request a look at the catalog. So the collection formats here are the thing. This is just within this one catalog. So you could potentially go and find any other stack catalog you wanted and put in the address here and do the same command, and it'll list the data sets that are available. Okay, so just within this one catalog, which is a particularly popular and open source one, it has things. So we have the CHIRPS satellite, which is precipitation data, more precipitation data. We have soil moisture. We have another soil moisture product. Here is precipitation, again, different satellite precipitation. Here is Landsat. Here's Landsat. Here's Maxar. Here is the Aqua or Terra products. So they have broken these though up into, this one is specifically the surface reflectance. This is the MODIS snow cover. This is the MODIS LS land surface temperature. This is different bands of the land surface temperature. Let's cruise down. NDVI from MODIS. Here is plant scope and Sentinel-2 data. We're going to deal with this quite a bit in our examples. Here's for you fire folks, here's the MODIS fire product. So all of these are available, housed on AWS in this one catalog for free, okay? So now we're back to framing our landscape. So again, that catalog is the thing that we could point our camera at. But when you look at this picture, right, notice there are trees that are telling one bit of story. There is a river that's telling a bit of story. There are mountains that are telling a bit of story. There's sky that's telling a bit of story. Every part of this is coming in to help you tell the story that you want to tell with your data. Eric, just to know, Eric's giving a, Eric, you want to hop in real quick and talk about this, finding out the memory limit?
Oh yeah, for those that are comfortable with using the terminal, maybe you've used top or htop before, but if you want to open up a tab in your discovery environment and click on the little terminal application, all you have to do is run the command top, all lowercase, and then you will see your running processes, as well as the very top, there's an MIB mem line. It's going to show you how much total RAM you have, and it's close to megabytes. I can't remember, it's like maybe bytes or something like that. That's going to show you how much total RAM you have and how much you're currently using. So some useful to look at while you have processes running to see if you're quickly running out of RAM or something like that.
Thanks, Eric. Appreciate it. For those of you who are following along, the new render is finally done. So if you just hit refresh, it'll pop up the one I was hoping we were going through today. And the main thing that you're going to see changed is that the DEMs are going to show up a little better. So here's the DEM, here's the slope, here is aspect. So let me go back just a second to show you, because these weren't working first. So This one went fast or even, 4.6 seconds. It created the entire DEM for North America. So again, that's mind-blowing. Here, from that, we then calculated, and it took a lot longer. It took 53 seconds to just calculate the slope, but then we had the slope, and then we calculated the aspect. And these, again, are just for one function. This is in the Terra package, and it's called terrain, and you just ask for the slope. Now, boom, we can create our very first data cube out of those three. So we just concatenate those three. We take the DEM and the slope and the aspect, and we have created our first data cube just out of those three things. So that's a pretty simple data cube. We don't need to save this, right? If you save this, this is really big, and it's probably slower moving it back from your memory, back from your drive, back into your program. It's probably faster to just leave it as these three plugins that just re-pull this thing each time you're about to use them. That's not always the case, but especially for these really big things, it could be a lot faster to just mount them. Notice where it talks about the sources of the three layers. The first one is an actual TIFF. This is the one that we plugged into. So it's saying that first layer we made from TIFF, but then that second layer, the slope one, we made from memory, and the aspect we built from memory. So so we had to actualize those onto our computer, but then they built each other really fast. Okay, now let me catch back up with where I was at down here. Okay, this has some of the description I was hoping was in there in the first place, to talk about Stack and talk about element 84's Earth search on Stack. And this is going back to Tyler's question of like, how do we know which things are set up for this? Well, Stack is supposed to be the catalog of things that exist. You can go outside of Stack, people, and find all these files. And that's the one that I showed you in the first one. That was one that was not part of a Stack catalog, but you can go and just download it like anything else and just see if they error out. You can also look at lists of VSI compatible. So a lot of places, if you go to their metadata, they'll have a thing saying BSI, just a column saying BSI and yes or no on whether it's compatible all the way down. These are those collections that we looked through. And we were here talking about deciding which data to bring in. And that is what, so the actualizing this, looking at a scene, right? In Ansel Adams, it was just pointing it towards the scene. We have to code this in. So we are saying, okay, here is the address I want to pull from. Notice that I switched from V1 in the early example to V0 in this example. It doesn't really matter. I'm just pulling from a slightly different catalog, and if you look in the metadata, this has 22 million items. So it's Sentinel-2 cogs, Sentinel-2 data, and there are 22 million items, indicating way, 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 way too big for our computer. There's just absolutely no way you could download this whole thing. So the first thing we do is just make a virtual collection of the things that we might want to download. And this is what I'm saying is framing in your scene that you want to take a picture of. So we're saying, okay, first take S, which is my connection to the stack. So here I've plugged in, I've just sort of linked to the website, the Stack website. I haven't done anything yet. I've just like sort of pointed my computer to that. This is the piping, this little piping function just says stack all these functions after it. So I plug in and then I say, okay, I want you to search everything I want you to search within that catalog for the collection that I want. And I decided I wanted Sentinel-2, and these are the L2A cogs. So these, when a satellite collects its raw data, that's L0, then that is sort of synthesized into a higher level abstraction, which is L1, higher level, which is L2, higher level, which is L3. So the higher this number, the more analysis has happened on those data before you're getting them. So L2 is pretty raw. You're just getting sort of, they've been spatially projected. Here, I made these bounding boxes earlier saying, what is my area of interest? That's when we were having the area of interest discussion. And so if you look through, I'm just giving the 4 different quadrants, the top, bottom, left, and right of what that area of interest is. So what is my collection I want to look for? Where is my area of interest? And what is my time span? Here, I'm just going for 1 day from the 15th of May to the 16th of May in 2001. And post request is the send it off and see what they get. And then this gives me a progress bar so I can see how fast things are going. Okay, so I did that. I built this search. From that search, I then am going to assemble a collection. The question is about how do we get that list? It is a function that you call right here, called collection formats. So once I put in this get request, so I first did this line of code and that plugged in and got the stuff. And then I ran this function to read that file that came in. And that file tells me all of the possible things. So it's this collection underscore formats. In Python, the Python function is just a slightly different command here, but you're going to get the same thing. But again, we just said, okay, I have this collection out there in the world. Tell me what's in it. And then this is the list it returns. From those, here's that Sentinel. Oh, no, here's the Sentinel 2A right there. Okay, so back to here. First, we searched. So this was, okay, what's in that catalog? Second, we build our collection. So see this stack image catalog? This is saying, okay, from inside Sentinel, and you have to go look at the metadata to find out all the things that you might want to pull from here. You're saying, okay, the assets that are in Sentinel 2A, it has a bunch of spectra. So these are different bands of spectra from the multispectral sensor on Sentinel 2. Each of these are at a different frequency, and they're just giving you a different reading on that band. And then this is sort of a data quality metadata field, and we're going to use that later. Thank you. Sibeli is correcting me. Sentinel L2A is the surface reflectance data. Okay, so here we...
Not
go ahead,
correcting, not correcting, just adding.
Okay, no worries, no worries. Sibeli, do you have any notes on Sentinel 2 that you want to note that you would?
No, I was just like giving that information about like this is the data, the actual surface reflectance, because the levels that you described it before rightly. So I'm just like adding that information.
Great, thank you, Sibeli. I appreciate it. Sorry, I muted myself. Okay, now we're going to actually build the collection. So we searched to find out what was available. When that returned, we came and said, okay, we want these assets. We're going to build them into a collection. And one thing that's cool about when you build your collection is right now is your first time to run big functions, like actually do operations on that collection before we move forward. So here, what I've done is, so in my collection, I first have taken item features, which are the things that were returned here. So I called that items. And so the things that were returned in my search, I'm going to give my search results to that collection. Okay, I'm saying, okay, here's my entire Google history, or my Google search for that thing. I'm saying, okay, from those search results, give me these assets that I've listed here. And then run this function. So I'm going to do a filter on those. So this is like, if you imagine a Google search, you've made a Google search, you've gotten a bunch of results. You then subset those results by your assets, and then you can subset again. And so the subsetting we're doing here is saying, oh man, there is a whole separate cloud cover data set associated with this that you're not seeing in the assets, but it just each individual day is tagged with how much cloud cover was in that picture. And so you can come and say, well, only give me pictures, or get rid of any pictures with, only keep pictures with less than 20% cloud cover. So if there's more than 20% cloud cover, just throw the things away and don't even return them. Okay, so we've given the search results, subsetted, and we bundle that all into our collection. And you can think about this now as the scene of landscape that we've framed in. We haven't taken a picture. We have just decided what we want to look at, what time we want to what day we want to be there, what we're trying to capture. We've sort of built our scene. And that can be a long and complicated process in and of itself, as we saw from the David Yarrow photo, right? Just getting the scene set up and deciding what you want to go in can take you a very long time. So give yourself patience. But actually running this code only takes half a second. Okay, so I have built that collection, and this is what it looks like. So this is an object now in my code. I have this thing that I can pass to other things and need to pass it to other things. And in there, it just has sort of this list of search results that I have found, the scene that I'm looking at. Now we have to get our camera ready. Okay, so here's back to our Ansel Adams camera. Here is his film. Right, he is pouring chemicals on glass in the morning to get them to build the film. That is your end goal. You, as the scientist, you're trying to make a data cube at the end. That can be flat like a piece of film, or that can be multiple layers. But the artistry is what hits the film. What's the very end point? The camera, this is our tool for modifying those data. So en route, coming towards us, we actually can change anything we want, right? On a camera, you can put filters, you can put different lenses, you can run light around corners and in the camera, you can do all kinds of crazy things through mirrors. And so you can manipulate the data in lots and lots of ways before it hits your film. The old way of doing this would require you getting like lots and lots of film into your computer ahead of time. We're going to try to just modify it while it's coming in, okay? So the VSI is from GDAL. GDAL is a computer package that has been around for a very long time that runs almost anything you can imagine that you've ever done in spatial analysis. So anytime you've loaded any spatial data or done anything like a union or an extraction or anything, this is GDAL. Now, GDAL has had this problem in the past where the data would come into your hard drive and then you go up into Python and you go through GDAL in Python. And so again, you have to have all of that data coming in through the machine, which slows things down. And a lot of us spent a lot of frustrating hours trying to get GDAL to work in cloud environments in that system, and it was really difficult. And so GDAL, in response, actually changed the way their software functions, and so they could put it on the server side. And so then when I say you can do anything that you have historically been able to do in a GIS, you can now do in route. That's because GDAL has essentially made a camera. So when you're looking at this, think of this as a GDAL camera. It takes any information from that scene and modifies it in any way that you can imagine that GDAL would normally modify anything. So this is reproject it. This is change the extent. Now, the collection, which is the scene we're looking at, needs to be larger slightly than the picture you're going to take. If you can't see it, you can't take a picture of it. So often an error that people find is that they will make their collection for one day, and then they will try to set up their camera to do a 2-day picture, and it'll just fry out and say, well, you didn't build your collection big enough to capture that picture. Okay, so this is just the conceptual rule is your landscape, which is that collection that you made from the cloud and assembled from your search results, that needs to be larger than the picture you're going to take. Okay. So we set up, it's called a view window, a cube view window. And we set up a few things. Here's the spatial projection. So this is, I was telling you there was some confusion with spatial projection. Here, I gave it a bounding box with that really, really popular spatial projection I was telling you about. But it returned those results in a different spatial resolution. And I just have this note that this is harder than expected because you don't usually know what projection they're giving you back. And so this can be a little bit of trial and error, a little bit of, sort of getting things and seeing the projection they're in. But this can be a little tougher than expected. I would try to just use the code that I have and see if it works. Okay, but again, we're setting up what our picture, we're setting the settings on our camera. So this is, the projection would be, what is the exact morph of the film that final map's eventually going to be on? How big is a pixel? So here I have 100 by 100. You can go down to 1 by 1 or 10 by 10, or you can have them mismatched, and they don't have to match the original data set. And this is, again, one of the sort of most magical steps here, because we can set this on the camera. Now you go take a picture of 4 different data sets, bring that information in and modify it. They're all standardized at the end. So a lot of us, if we think back to the bad old days, you sort of had to bring all 3 data sets in, transform them all in your machine so they're on the same projection, and then they could go together. I have this question about where do you find the CRS from? And you essentially ask, so you use the CRS function and it tells you what something is projected in. Usually here you have to fiddle around a little bit. These I found in the documentation. So when I say this is harder than expected, it's because there's not an easy way to just look this up from the data themselves. So I think this took me several hours to sort of work through what the actual right one was. So normally, if you have the thing in hand, it's pretty easy to find the CRS. Here, it can be a little trying looking through documentation to try to find it. So let me try to find a better answer than that. All I can tell you right now is it's a little harder than you want it to be. But I'll try to find a better answer than that. So here's the size of the pixel. You can make this tiny, but that can make this really big. So I guess this is, again, where the art comes from, is like, you have to set up your camera to be proportional to the film you're producing. So if I make this, okay, I have this question about masking. We're not masking yet. Masking is one of the things that we can do in the operation. A mask would be something like maybe putting a tiny piece of tape across your lens so light can't get through that. So maybe if you have coastal data and you want to mask out everything that's ocean, so it's just like an NA rather than something else. These are, so you can have, let me pull up the documentation for this, because you can specify, the question here in the chat was, what is dx and dy? This is essentially as specified here, it's specifying how big, how many meters the pixel is. But you can have it being dividing or specifying the exact amount. Let me pull up the documentation. Okay, so the function is called cube. So the GDAL cubes is the library, and cube view is the function. As we go down here, you can use nx as the number of pixels. So based on the extent, how many pixels do you divide it up into? Or you can do the dx to say the size of the pixels. And I say so but the size, quote unquote, depends on the projection. So if you are in meters, then this would be like size in meters. If you're in degrees, then it would be size in degrees. And so the projection sort of tells you a little bit about what your size is. Okay. So you're going to want to probably spend some time familiarizing yourself with these few settings and how they change your data. But I think the key thing would be here is that once you set your cube view, just have it the same for every picture you take, and then all of your outputs are automatically standardized. So this can take a while to set up. This can be a little laborious, but once you get it, it's pretty nice because it standardizes all of your outputs. Okay, so this again takes a fraction of a second to build this because you're not getting any information from the cloud. You're not doing any processing. You're just going and building your little viewfinder camera. There are two settings in here that are really important. It's how do you want to aggregate your space? So if the pixel sizes in your collection are different than your view, it's automatically going to reproject those to something different. If it needs to combine multiple cells, multiple pixels into one pixel, what mathematical operation would you like them to do? The same with time. If you need the time to be shortened, maybe you build a collection out of a day and a half and then you only ask for a day and there's some averaging on the borders, or you say, give me a monthly average, then, and so here, the time that I've given, they have some time codes. This is the monthly average. So this is the P1 is the average and across the month. And so you're saying, okay, how do you want to deal with those? Elsa was making yeah, Elsa, do you want to make your point real quick?
Yeah, sure. I think that where I and students often run into trouble with that aggregation function is when you're dealing with something like land cover classes that's categorical. So we have like class 4 and class 13. And if we average those, then that's not going to mean anything anymore. So you'll want to have an operation that gives you a whole number in that case, like the median. So yeah, just watch out for that with categorical data.
Yeah, the average of A and C is not 2.
Right.
Okay, perfect. Really, really good point. Okay, and now it's time to take the picture. Okay, so we have done the hard parts. We have done the setting our frame and setting up our collection. We have built our camera with the standardized output that we want in the end. And now we take the picture. So what do we have to do? We have to give it our collection. And then we are going to use this function called raster cube and give it our view. So the V here is the camera that we built. So it's saying, take this collection and build a raster cube using that viewfinder. And it takes the picture. Okay. Now coming in, we have not hit the film yet because of the beauty of the way the system works. You don't actualize until you do something like write or plot. Okay. So with the remote connection, we take the collection, we build a virtual data cube. So we've now built the cube. This is the information coming through our camera. And now we can do operations on it before it gets to us. So this is where you get a ton of power of like getting a bunch of computation done before it hits your RAM. And so here I've calculated NDVI. So by selecting these 2 bands, sticking those bands into a function and giving the column a name, this is all happening while the light is coming through the camera. Then finally, I do not have to write this. This was to save. So now that if we want to save this, we can make it into TIFFs. Here, oh, this is just me showing you specifically how to make a raster stack. So we're going to convert. So those things, that light is now actualized on the film as TIFFs. And we stack those into a raster stack and we get a raster stack out. And that whole process there, right? So this is for Boulder County, for the entire county. It took, nope. Well, did we do county here? Did we do, let me check. Yeah, we did Boulder. Yep. So for the county, it took 4 minutes. So that was 4 minutes to pull all of the spectral data, the lens reflectance data, and calculate NDVI and write it to TIFF and stack it. All took 4 minutes. Okay, so there are two different formats you can save as. There is raster style format. So this requires 3-dimensionality. This requires it to be a cube shape. So you're going to have gridded data stacked, and those gridded data are going to be in TIFF format. But there's a more flexible version called stars in R. This I think is ZAR in Python. And this allows you to do different types of data. So somebody asked last week about combining point beta vector data and raster data. You cannot do those as raster without actually converting all of those different formats to a raster. But stars and ZAR let you have more flexibility. So you can actually you can have more than 3 dimensions, and you can have different types of data stacked on top of each other. Okay, let me show you, because I'm running out of time. Let me make sure we get through the last couple of points. Extracting data. So from that same collection, from that same view, I select bands. This is all virtual, just saying like out of that cube that was created, these are the bands that I want. And now I can do this extract geom. So I'm going to take that polygon of Boulder County and put it over, and I'm going to extract the values out of every single pixel. Here is just renaming those because they are spectra. These were the spectra, the band names, and I want to put what the actual frequency was. Okay, Elsa's correcting me that X-ray can do a bunch of different formats and sources. Okay, so I extracted those. I only print the very top, but this created a 2-dimensional data frame. So this is really, really long. This is a list of every single pixel, what time we collected, and then what the measurement was for every single pixel. And so now you can go and print those bands. This only took 1.7 minutes because I didn't write it, right? This one up here where it took 4 minutes, that's because we decided to write it to our hard drive. And as soon as you write it to your hard drive, now you were slowing the whole process down. So it took 4 minutes because I decided to write it. Down here where I don't write it, it only takes 1.7 minutes. So I can make it twice as fast if I just don't need to actually write this thing to disk all the time. Here we can do a whole time series. So the last one I showed you was just 1 day. Here I want a long time series. So it's from 2020 to 2022. There is a function that I don't have in here, which is called reduce time, which is another one you can add in here if you want to do more complicated time reductions than I've done. I still have that 1 month average thing built into the camera view, which is down here, the P1M, right? This is in my camera view, I'm just specifying what the time list is. But even after you've taken the picture, if you need to reduce it more, you can do that. So here, let's just take another picture exactly like I did before. Here's my raster cube function. Select those bands, calculate the NDVI exactly like I had before. Except now let's animate it as a GIF. And so here, let's see how long this took real quick before we go look at it. So this took almost 5 minutes, but that was writing a plot for every month. So we get the NDVI animated over the course of 2 full years. That gray in the beginning is right when the sensor came on. So I found the very first instance of the sensor coming across, and it only that month came across that little bottom corner wedge. Okay, when you want to write, when you do want to finally save something, you can save in two different formats, netcdf or that TIFF. So I showed you above where it was write TIFF, and then another way to do it is write netcdf. They also have different compression levels that you can choose if you're having trouble finding the memory, finding the disk space to actually save these huge things that you're sucking in. And then this was, yeah, it's pretty easy to, so here I've done one collection for 2020, right? I'm again searched, built the collection of Sentinel data with the bounding box, with the time period, and asked for that data and got some data, got some items back that were just 2020. Did a separate one for 2021, ran both of those processes in parallel that you saw before, calculate NDVI just like I did before, and now you can just subtract them. So within the STARS library, they have things like raster calculators where you can just subtract, oh, here's the actual, sorry, down here. So you just subtract one versus the other, and now you can get max difference in NDVI between the years. But these objects, again, are completely virtually plugged in, but you can bring them into all kinds of functions that we normally use and use them as if they already exist on your computer. Okay, so that has burned up almost all my time. I have 5 minutes left. And with that time, I'm going to show you some of the data that I've made available to you with some code. The ones right here on the sidebar, you can see are really flood specific. And most of these only have R code right now. I'm going to go through those in just a second. Let me put another link up though. This is our data library from the summit. And then I see, Tyler, I see your question. Let me go through a couple data sources and I'll try to answer your question on my way out the door. Okay, so first, if you go to this, on the sidebar, you're gonna see a lot of different data sets organized in groups related. The organization doesn't make a lot of sense for this context, but don't worry about it right now. But in here, you can find some, this is an example, native lands digital. This is how to get polygons of all of the native tribal land around the globe really easily. And the reason I want to show you this is most of these we did Python and R. Not all of them, but a lot of these have Python and R solutions in them. So feel free to look through these in terms of giving you lots of different data sets that you could potentially put in your landscape and ways to download them. As we go back to the data sets specifically for the hackathon, one is a flood inventory. So this is just a long list of all of the floods that have happened, where they have happened, and what their cause was. So here is point data of where those floods happened. Here they have how many died or were displaced. And so I did some plots on just the relatedness of dead and displaced as you got bigger. You know, something like we have a lot of low frequency floods, only a few high severity, and not very many super high severity. But when you get to really high severity, you get a little bit more higher levels of displacement. So the other thing I show you here is how to make a time series. So things like breaking down the composite time series of flood data, trying to detrend them and find out, oh, well, there really seems to be a pretty strong seasonality to when floods happen. Here is future projections of floods. Okay. Flood event polygons. So this is a way to actually get the polygon of different flood areas or different severities or different numbers of dead or displaced. If you need river geography, so you actually want to pull just the vector layer for a particular river you're looking at, you can do that from OpenStreetMap. Here are lakes, and then you can combine the rivers and lakes together. Hydro basins, the original data set, the original website I showed you at the very beginning of the lesson, it has a lot of great data on. So, yeah, let's see. This is like what the order is, like how high is it in the tributary in the watershed. So here are headwaters all the way down to tailwaters. The DEM we looked at before. Here is one where, so I showed you that some of those original data could only come in at 15 seconds. If you want to do higher, you want to do those 3-second ones, you can do it through a slightly different system. You just have to tile them together. And so this is me showing you how to pull the individual tiles if you need the higher resolution stuff. Again, these are showing you different informations about the basins, different information about, so this is not necessarily flood data. These are great river data, where water would flow data, how to calculate how bad a flood is, those sorts of things. Okay, Neon has a bunch of great lake data sets. The thing I want to show you here to get back to Tyson's question about what is sort of the ideal structure of a data cube, okay? This again depends on the question you're answering and that picture you want to take. So here we have Neon data. You see they only go back to 2015, but they cover a bunch of stuff and they cover a bunch of sites, and that's wonderful. Now, if you combine that with LTER data, LTER data, they only cover a couple places, but they do it for a really long time. Neon data cover a bunch of places with really high fidelity, but for a little bit of time. And so fitting those two together into an ideal data cube actually has a bunch of philosophical questions, not structural questions. It's sort of, well, do I want to make the cube this whole area and have all of this blank? Or do I want to just look at this part and just compare the data here? Or sort of how philosophically do I compare those two data types into something that's a cube? Now, what is the ideal cube? Computer AI, the thing that you're going to plug in to look at this wants a completely uniform, completely filled in structure. So any parts of that cube that sort of jet off into some new direction are hard to interpret on why that would be. It's best for an AI to be able to look at this cube and say, okay, as I scan it different directions, I see different things changing in this way, and I can gain different inference from that. So ideally, you want a cube, and that is our goal. But you can see how hard that is. There's so many decisions, so many compromises that have to go into creating that cube shaped thing at the end. Okay, there was a question about environmental data to predict water quality. Yeah, there are a couple of those. So in the Neon River ones, they have sensors above and below a bunch of their sites. And so you can get things like dissolved oxygen and dissolved carbon and things from the Neon sites. The EPA, here's a water quality data portal. So this way you can get things like how much ammonia was there. And this is one where there is R and Python code to get this. USGS water services, these are the places to go generally to find out what the flow was, how much flow was there over time, and when were the peaks. Ooh, this one's broken. I'll fix that. The species occurrence uses iNaturalist. There's a package that helps you pull species occurrence data. Neon, this goes to an external link, but they show you how to get the LiDAR data from Neon. So if you wanted to look at sort of physical structure beyond what the DEM can give you. And Neon biochemistry also has sort of, these are the terrestrial ones to match the river ones. So if you wanted to say, okay, we see a ton of carbon, we see a huge nitrogen pulse in this river on this date, you could then compare it to the terrestrial measurements before that to say, okay, yeah, in this flood, it swept a bunch of that nitrogen off of the surface and pushed it into the water. OpenStreetMap, we already played with that a tiny bit. This just shows you how to get those. layers for OpenStreetMap. US Census, if you want to find out, you know, sort of poverty estimates or demographics on who lives there or how long they live there, how many grocery stores they have. And then the remote sensing one is the Sentinel stuff that I showed you in the main lesson. This is just a longer, more involved version of those Sentinel data. So I think that I have burned through all of my time. I'd like to give people like 2 or 3 minutes to ask questions before I pop out of the way. But I also want to reassure everybody that I know we cruised through this really quickly. Just trying to give you the philosophy of what we're doing, give you a little bit of tools to point you in the right direction, but then have you go and sort of play with these throughout the hackathon and know that we'll be around to help you get them set up and help work with things when you have a problem. So let me open up for questions for about 5 minutes, and then I need to pass off the torch to our next fearless leader. Hey, Tyler's asking about the difference between zeros and NAs. An NA is filling the space. So, and usually NAs are preferable unless the zeros are confirmed. So if most data scientists, when they see a zero, think that you have confirmed that that is a zero, that zero is the actual value of that data, not of that datum, not that those datum are missing. So don't put a zero unless it's confirmed as the zero, and otherwise put an NA because that completely fills the space. All right, let's go take a break. Let's give everybody a bio break, 5 minute. Let me just pass it off to Nate and let him run the breaking. But thanks everybody, I'm around. We'll see you at the hackathon and try to answer all the questions and deal with all your panic as much as we can then.
Yes. Yes. Thank you, Ty. Give it up for Ty, our very own friendly neighborhood data scientist. We are lucky to have you, my friend. Yes, thank you. Great job. Remember, this is all recorded, and so you can go back and watch that stuff. And we're going to be here to help you during the hackathon too. So don't think like you have to have absorbed all of that information that Ty just gave you, because we've got resources for you. So give Ty a big shout out. Why don't we do this? It's 10:23 Mountain Time on my clock. What do you think? Rachel and Virginia go until 10:30, 10:35 on a break. How do you feel? Make sure we want to give Ayub enough time.
Good 10 minutes, so 10:33.
10:33. I love it. 10:33 Mountain Time. We'll come back, and we'll get started with the next piece. Thanks again, Ty.
So the first thing we would do, I will send my GitHub repo in the chat, and you will have to go and clone it. Okay, let me start here. Great. Okay. 1 second here. I just want to grab the chat. The window is still all right. Is it better this way? Okay. So I sent the link on the chat, and you just have to follow the steps I'm doing now. I guess you might be already familiar with that, but just in case. So the first thing we want to do while I'm doing the presentation is to execute the script prepare environment. So this is going to install the packages that you are going to use. So just do bash prepare underscore environments. It's going to take some time, but we don't have to wait for it. Once it starts, we're going to move forward. If you have questions, feel free to send them on the chat. Yeah. I'll try to answer if they're relevant to what I'm doing. If not, I'm going to answer them later.
I have just a quick question. Is the intention that people will be following along with this or watching you and finding out later? Okay.
Yeah, they can do them later. So we just keep up or just watch? Seems like it will keep up.
Okay. So if folks
Okay.
are following along, then you can use the GitHub extension over on the left-hand side to clone that repository if you didn't catch the command. It's like the little GitHub symbol all the way on the left, yeah, or in the Git menu.
Okay. All right. So I'm going to start while this is done. I'll go ahead. Okay. So I'm just going to do yes here. And I'll let it do its thing. So this is going to be a dense but quick presentation just to give you a flavor of what machine learning is. And at the end, it's going to be more like desktop environment should we be using? Let's say that again. We want to keep up with yeah, just gonna be Jupyter 1, but we're not using it. Okay, for now. Okay. We've already started that. We're going to resume that later when the packages are being installed. So so the theme was more like artificial intelligence, but we are going to talk about a subset of artificial intelligence. The main difference is that artificial intelligence is a more the black screen is just me.
Yeah, it's not. Yeah, I also just see a blank screen. Maybe you didn't yet select the window you were sharing.
I'm doing share screen. Okay, 1 second. Okay, sorry for that. Let me just move to something else. Okay, I'm just gonna use my desktop for everything.
So in the meantime, Elsa, would you show us how to clone the repo one more time so that everybody can follow?
Yeah, 100%. So we're going to head to the discovery environment here. Let's see, I've already got this analysis, but if you're on the discovery environment, which I'll put this link in the chat in case you've forgotten, de.cybers.org. You're going to log in and you're going to go to the apps page, and probably any of these Jupyter Labs will work, but we're going to go with this Jupyter Lab Earth Lab. And click through here. And then once you have clicked through, you will have, like I do, an analysis running here. So I'm going to go to that analysis. And here's my Jupyter Lab. So we can head over to this link on the side, or like I was showing, you can go to the Git tab. My mouse isn't great, so it's not always clicking on things when I say. And then we're going to go ahead and clone the repository. This link is in the chat, but I'm going to copy it and put it down in the message here again. This is an HTTPS link, so you will not need to set up the authentication yet here. Okay, so I'm copying and pasting this Easel AI link, and I can go ahead and clone. And now it shows up in the main folder. And we can see all of these notebooks. And then I believe Ayub was running this prepare environment.sh. So you'll go here into the terminal. You'll notice that the path in my terminal is the same as the path here in the file browser. And so I can go ahead and run this command. There's a couple of ways to run shell scripts. One is to use the source command. Sometimes /prepareenvironment.sh would work too. But here this is going, and that's going to take a minute. So Ayub, how are you doing?
Yeah, let's go.
Let's go. Okay. Perfect. Yeah, I can see that now.
Okay. Okay, so let's get started. Thank you. So I already done that. So as I was saying, the term artificial intelligence is more general. Artificial intelligence is about developing software that is intelligent in a way that can reason, learn through new complex tasks. The term intelligence is more like a philosophical thing, but there are two basic approaches to define intelligence. First one is human, means that software or machine is intelligent if it can make decisions similar to, comparable to a human. You might be familiar with the Turing test. And the second one is the rational approach, which means that the algorithm should make the most rational decision. And machine learning is one method of developing such algorithms. There are three methods in machine learning: supervised, unsupervised, and reinforcement learning. I'm just going to cover supervised and unsupervised. In the repo, you're going to find a folder called RL. So that one, if you want to check it later to get familiar with the notion of reinforcement learning, but it's a bit too technical to cover in today's talk. This is like a sketch of the schedule, but I'm not sure we're going to follow that. We already lost like 15 minutes, so we'll see. So when talking about supervised, the supervision is coming from what we call the labels. So imagine we have data sets. So a data set is just some number of tuples that we are going to denote by x1, y1 until xn, yn. So these are the samples. And x1 here is going to be the features, and y here is going to be the labels. So the goal in reinforcement learning is we assume there is a function that would map the features to the labels. We don't know what that function is. We don't even know if it exists. Why? Because sometimes you can have, in the data set, you might have the same features, but with different labels. Usually machine learning, we remove that assumption. So it's basically, we make assumption that the data set is kind of consistent. So the same features cannot have the same label. And the goal here is to approximate these, or find the best approximation for this function. And the approximation quality is evaluated based on some loss function. Okay, so the first choice that we do in supervised learning is that we have to choose the set of functions that we are going to find the best approximation among. And the second thing is we have to choose the loss function. And this loss function is what's going to tell us whether the approximation is good or not. And even when you define the same class of functions and the same loss, then you have so many algorithms that you can use. Each one of them have its own guarantees. So one of the simplest tasks is, or the common one, is the classification. So in that case, you're given a set of features. In this case, it's going to be the cat images, and you are trying to classify the image. The second one is, instead of just classifying, you're also looking at, you're trying to find the region, the minimal region that makes that label relevant to that image. Then you have also object detection. In that case, it's not just one label per feature or per image. You have so many labels. And in that case, the label will be the region of the image and the object identity in that region. You also have the image segmentation. So here in classification, you have a discrete label. In localization, you have a discrete one and the continuous one, which is the coordinates, and vice versa. So it's not like a binary dichotomy of the nature of the data sets we're working with. You can have all type of labels in the data. You also have natural language processing, and this is what we call the sequence to sequence prediction. In that case, you have a speech, which is converted to other features. Usually this speech is very long. It means that you have an audio file and then you have certain thousands of frames per second. So what happens there is that you first do the feature extraction, and then you use the some machine learning model on top to match it to the text. So in this case, the label is the sentence that's being uttered in the voice. Instead of taking the speech as input, you can also take the other sentences as input. In this case, you're doing translation. So here you're translating an English sentence to a French, to French. In all these examples that I've given, there's a common theme to all of them, and that's what we call the bias variance trade-off. So if we're given this set of data here and we're trying to find the best regression, there's also always this problem whether to find high bias, which is called underfitting. In this case, you're not learning the true structure of the data. Optimal one is what we're looking for, but the overfitting is when you are using a too much complex model that kind of fit the entire training data, but it does not capture the interesting structure of the data. So if you add another point around this region here, you're going to miss it. So the one on the left here, we say it has a high bias, and the one on the right, we say it has a high variance. And you can show analytically that when you optimize the bias, the variance becomes worse, and vice versa. So there's always this trade-off. In classification is the same thing, except here that you can see that the overfitting is about finding a complex boundary between the two different classes. Perhaps the most simple example. Someone, give me 1 second. Let me just check the chat. Okay. Perhaps the most simple example here is classifier called decision trees, where you can have different type of features. Okay, so you can have continuous features, you can have discrete features. In this case, the continuous features are the age and the weight. Actually, you can argue they are discrete, but let's just assume they are continuous. And then the discrete one is whether the person is smoking or not, and the label would be whether it's low, whether they have low or high risk. And the same thing here, you might have certain threshold at which the model can overfit in a way that if the tree goes too deep, you might have a kind of a binary tree that will end up with one person at each final node, but it does not mean that the model is doing well. The second one is perceptron. So the name might be kind of scary, but it's not. So what happens here is just you take the features and you multiply them by a matrix. Okay, so you just take the features, multiply by certain weights. In this case, we have 4 features. For each feature, we have the corresponding weight, and then we add the bias. And in the perceptron, we're doing a classification. So if this value here is positive, we say it's 1. In this case, let's say it's high risk, and 0, it means it's low risk. Sorry, I jumped too many things. We were here. Okay. I'm just going to introduce the dataset that we're going to work with. It's going to be a simple image classification of cats and dogs. And there is a plot twist that we're going to see later. But the question here, how do we deal with images? I've chosen this type of data because I assume you're more familiar with spatial data. Just give you an example of how to work with images. So with images, we have this concept of what we call convolutions. So it's kind of an extension of the matrix multiplication to spatial data. So here you can assume that these are the pixel values of the image that we are going to work with. And here what we call kernel, or you can call it filter, depending on the notions you want to follow or the Python library that we want to use. So in this case, we have already initialized the weights. And the way we compute the convolution is we start with the upper left corner, and we do an element-wise multiplication of these. So initially we start from all the top left, but assume that at a certain level we reach this region here where we're going to do the multiplication. So the result of this convolution at this point here is just going to be 2 multiplied by 1, 2 multiplied by 5, it's going to be 10, and then we do the same thing for all of them, and we sum. So one thing here to note is that the input image and the output image have the same shape, and we are going to see why. So here, if you want to do the math, just simple multiplication and addition. So in this case, the output of this convolutional operation between the input and the filter is just going to be 198. You can check later if the math is correct. However, the output can also have different shape than the input. So the difference here is that we have what we call a stride. So a stride here is that it means that we start with the convolution at the top left, but then the stride here is 2. It means that we are going to jump 2 steps, so basically 2 columns, and then compute the second convolution, okay? And the same thing vertically and horizontally. So we have the, sorry, we have the violet. We have the violet convolution followed by the blue. So the third one is going to be the green, since we reached the right bound, and then we do the stride 2 steps to the bottom. And the same logic as before. So these are the element-wise multiplications, and then we just have to add everything here. So in this case, it's going to be 2. Here it's going to be 5, and yeah. So you see here that we almost cut we almost reduced the size of the input by half. And the reason here, or the factor here, the stride is 1. Previously, the stride here is 2. Previously, the stride was 1. Okay, so that's why we keep the size. When you increase the stride, you reduce the size of the output. So now you imagine that we take the image, we apply the convolution, and then we have the output. And in this case, in classification with neural network, the neural network is going to, when you have a very large image, you want to use a stride larger than 1 to reduce the size. But sometimes if you use a stride 1, you're taking too many small steps, and you might be learning redundant information. So imagine I have a high resolution landscape picture. Stride 1 is just 1 pixel. You're not actually moving anywhere. So it's more like a parameter that you want to tune to find at each steps. If you jump from one region to another using a stride, you're going to have more different features than the previous region. Okay, going back to modeling the problem. The output of the neural network in this case is going to be probabilities. It's going to be outputting the probability that the image is a cat and the probability of the image being a dog, okay? So here imagine that the label is 0 if it's a cat and the label is 1 if it's a dog. And the loss function, what we call the cross entropy, this is the more general formula, but you can just easily just write it down much simple. So if the label is 0, then the loss is minus log p cat. And if it's 1, then the loss is minus log p dog. And we are trying to minimize the loss, okay? So it means here, since log is an increasing function, we're trying to maximize the probability. So it's as simple as that. If the label is cat, we're trying to maximize the p cat. If the label is dog, we're trying to maximize p dog. The question here is how to transform the output of a neural network to probabilities. And that's where we have the notion of activation functions. So after each time you apply the convolution, you apply the activation function. So in this case, you want to apply an activation function that will transform whatever the output is to the range of 0, 1. The most relevant one is sigmoid, okay? So the plot here is, it's always between 0 and 1. It never crosses these limits. But you also have other types of activation functions that might be relevant to whatever problem you have. Usually, we always add an activation function after each convolution or after each multiplication layer, because these functions add non-linearity to the model. These are basically the most famous one. So the tangent hyperbolic is just going to be mapping whatever you give it to -1 and 1. The ReLU is going to map it to positive range. So it means that if the output of a certain element of the convolution is -1 or -2, then it's just going to be zeroed out. The ReLU can have a problem here. It means that if you zero out everything, yeah, we're going to see that. So we said that the activations help by adding nonlinearity to the model. There's a second way of adding the nonlinearity and what we call the pooling, okay? So the pooling here, it means I'm applying some nonlinear operation. So in this case, we call it max pooling. It means that in this case, it's a 2x2 max pooling. So I'm taking each 2x2 region and trying to find the max. So the max here is 20, the max here is 30, and vice versa. So max pooling is interesting because there's no convolution that is equivalent to max pooling. It means that there is no filter that will allow you to get max pooling. Average pooling is easy. So in this case, you just take a filter that is 1/4 everywhere. So basically, you just sum in everything and divide it by 4. But for the max pooling, you can prove that there is no convolution that will give you the max pooling. That's why max pooling is more popular. So in neural network, the question there is, okay, so how do we train the neural network? And we have seen that the convolution there is the parameter. And as in, for example, regression is going to be the weight matrix. So in the neural network, we are using gradient descent. This is a very easy and nice function, but the neural networks are not really this nice. So you just use some batches to estimate some local gradient, and then you just follow the gradient wherever you're going. It's not convex. It means that you're never guaranteed to reach the global optimum. So it's always some local optimum that you are reaching. Okay, so we're going to move to the GitHub, the notebooks. So I'm going to move to the environment. Assume at this level you have everything here and that you have already executed the script and installed the packages. Yes or no? Any answers in chat? Yes. Okay. So we start with the supervised part. We just hope we're gonna have enough time to do some interesting things. Okay. NumPy is a package in Python where you can do all the linear algebra thing, matrix multiplication, even random probabilities like generating random variables. Matplot PyPlot is doing some plots. Yep. And then, yeah, the source. And then if you have some questions, just type yes to install the packages. Okay. Scikit-learn is a package that contains most, if not all, the classical machine learning algorithms. You can also do deep learning, but it's not really the specialty of scikit-learn, okay? So we're going to use it here for some utilities and to do some model selection. So I'm going ahead and start. Okay, so I forgot one thing, which is I have to do source download data. Should be really fast, so that's not. Once you do that, you're going to have a data set here that has the data that we are going to use. So let me go ahead. Oops. No, it is there. So this is, yeah, it is there. Okay, let me restart the notebook, I guess. Start the kernel. Okay. So the images are 256 by 256 of some nice cats and dogs. Let me just decrease. Okay. This is a random shuffle, so you might get different images depending on the server. It's a quite balanced data set, so the problem of label balance is not a problem. We're going to use Keras TensorFlow, one of the two most popular deep learning frameworks. The other one is PyTorch. One thing you can do when you have images is what we call augmentation. So we know that if we flip the image or rotate it or do some random rotation, it's still going to be a dog, still going to be a cat. So we can exploit these augmentations to kind of superficially, artificially increase the size of the data sets. So right here it's the same image, but we can generate up to 9 variations of the image. Why we do this? It's basically a way to avoid the overfitting problem that we have seen before. Okay. So in this case, you're saying, I'm not just looking at a certain point. This is very similar to the 2D plot that we have. It's like moving the dots slightly to the left or slightly to the right to force the model to learn something that is not very tight. Okay. So what's happening here is that I'm just creating what we call an input layer in Keras, or an input, and I'm trying to augment the data. So exactly what I have done here. And then I'm doing the rescaling. So the images are RGB pixels. So the values are going to be between 0 and 255. So divide by 255 to make sure that it's scaled down to 0.1. Why we do that? Because if the pixel values are too high, then the model is going to be very sensitive to the input. Okay. So this is where you're going to start playing with the sequential model happening here. So I'm telling I'm creating a sequential model. It means that it's a stack of different layers. The input layer, it tells the Keras that we expect an image. So the input layer here is telling the Keras here, we expect an input that is 256 by 256. Then we're doing the rescaling, and then we add in some augmentation to artificially increase the size of the data. Okay, this is where we start. Okay, so this basically the same type of convolutions that we have shown. 32, it means that I'm using 32 convolutions. Okay, so the input has 3 layers, and here I'm saying that I'm going to have 32 out in the output. I'm going to have 32 layers in the input. So what happens here is that instead of just doing the convolution on the red channel of the image, I'm also doing it on the green channel. I'm also doing it on the blue channel, and I'm summing all of those. Okay, so when I sum all of those, that's basically one filter, and I do the same thing 32 times. And this way, I move from 3 channels in the input to 32 channels. 8 here is the size of the filter. In the last example, we have used my so in the example I showed there, we just used the filter. This is 4 by 4. In this case, it's 8 by 8, and the stride is 4. It means that each time we're going to jump 4 pixels. Okay, so the input of this layer is going to be 63 by 32. Okay. And then we flatten these. It means that we take in the image that is 2-dimensional, and we just creating one vector that has all the pixels, just 1-dimensional vector. So it's going to be 63 by 63 by 32. Okay, that is what the flatten is doing. And then here we're doing a linear multiplication. So we're multiplying a vector that has the product of these numbers as the dimension, and then we're multiplying by the weights. And at the end, we're doing softmax. Softmax is a variation of the sigmoid, but when we are doing binary classification, they are pretty much similar. The same goal is to scale the output of the layer to a 0-1 region, and where the probability is sum to 1. Okay. So the task for you would be to add more convolutions, change the parameters. You can also use max pooling. So here, instead of showing the answer, you can also go to just Google Keras max pooling. There you go. So this is the max pooling layer. And as we said, the default one is 2 by 2. So if I want to add a max pooling layer, I'll just come here and do Keras layers max pooling 2D. I can change, instead of 2 by 2, I can do like 4 by 4, and everything is quite the same. So once I do that, layers. Once I do that, I can do the summary thing, and it shows me the layers and the number of weights. Since the augmentation, I have no parameter here. It's going to just be 0 parameter. And the convolution is going to be the weights of the filter plus the bias. And yeah. So at the end, I have almost 1 million parameter in my neural network that I'm going to use. How do you usually choose the number? Usually you just do what we are going to do now, which is we're going to split the data. We already done this. So in the model selection module in scikit-learn, we have the training data, and I'm going to split it to a training data and validation data. Okay, so basically you're holding part of the data to the side. And what happens here is that we're training the model. First, we do the compilation. This is the optimizer that's going to do the stochastic gradient descent. You can choose whatever learning rate you want. So that's the step size of the update. The cross entropy loss, that's what I have defined before in the slides. And the metric that we are going to monitor is going to be the accuracy. Of course, we have the cross entropy loss by default, and then we're just looking at the accuracy. Okay. So in the training, you specify the training data, the number of the batch sizes. So the small chunks of the data you're going to use at each time, because sometimes the data set is pretty large. In this case, it's not to just have 1,000 samples. It's not too large. But if the data set is too large, you have like 10,000, 20,000, 30,000, you can't do the updates all at once. It's too expensive computationally. So we do the stochastic one, means that we're taking 16 samples at a time doing the optimization. And the validation data is what we are going to monitor. So the validation data is not used for the training. This is more used to just see how the model does on the data that it hasn't seen. And the epochs is how many times I'm going through the entire training data, okay? Okay, I'm not gonna wait for all of these, but you can try to toy with those, and let's see who does the best. Okay, so one thing here that a lot of people, like beginning machine learning, people beginning machine learning, is that you just say, okay, I'm going to train on training on the data, and I'm going to monitor the validation data, and then I'm just going to choose the one that reaches the best validation accuracy, okay? But if you do that, then implicitly you are using the validation data to train your machine learning model. It means that you are using the validation data to find the best model. So it's kind of an implicit or indirect way of training. So that's why we always have another data set that's used called testing data or evaluation data. In this case, it hasn't been used to train the network or find the optimal weights, and that's your real the real test that you'll be using. So in this case, I can see that the validation accuracy and the test accuracy are pretty close. If I go to the test, I'm getting like 95. So it's slightly worse than the one I observed during the training. This is just some function that I'm using to display some examples. Okay, so we have an intrusive, we have an imposter cat here. Yeah, that's probably one of the ones that we have missed. Okay, we have quite a few here that's doing not good. So why are we getting different accuracies in different runs? Because we have the random augmentation in the stack of the model. I think there was a way you can do model. I think, okay, let me just retry. Oh, sorry, it's accuracy, it's 1 on the 10 samples. So I'm using the first 10 samples. I'm using the first 10 samples here. So that's why it's giving these. Okay. Since the dog, if the probability, else cats. Yeah, good. Nothing weird. Now something is off, right? Something. Yeah, just labeling everything cat, even though I have an accuracy 1. So something is wrong in this code here. Doing a model hat. Let's see if someone can figure it out. Yep, it should be 0. There you go. Okay, so we're doing good on the 10 samples here. Let's choose, you can choose any random number of samples. Oops. Just go from the 10th one to the 20th one. Yeah, so here we're missing 1. Yeah. So this one isn't classified as a cat. So there's something wrong, right? And on the test data. The question here is to try to find why the classification is wrong. And in deep learning, that's a pretty difficult task, because the neural network, you can have multiple redundant features, and you can also have some jumps when you are looking at the output of the networks. Depending on the activation function, for example, if you're using ReLU, you can have region where it's basically always cat, but then if you move slightly to the left or to the right, you can have something that's called that's considered dog. This is what we kind of known as the adversarial examples. We're not covering here, but there are so many ways you can trick the neural network to predict what you want without altering the input significantly. The augmentation is one way to avoid this. So in this case, we did with the flipping or rotation. You can also add, sorry, you can also add noise, random noise to the input to counter that. Okay, perfect. Can the background context be taken? That's a plot twist. We're going to come back to that. Perfect. I'm going to move to the unsupervised learning part. I think I gave kind of flavor of what supervised learning is. How do you usually choose the number? 32, I already answered that. The Seneca set of pixel colors or object shape to segment objects. So you can actually show in machine learning that the first layers are more attentive to the color, but the more convolution you add, the more abstract the learning becomes. Okay, so one thing to see that you can see like filters in convolutions. Yeah. So this is basically the first, I would say this is the bottom part of the convolutions. So they are more like detecting the colors, but the deeper you go, you start looking at the edges as well. So it's not just the color of the pixels, you're also looking at the edges, the different directions, like an edge from the left to the right or the top to the bottom. Yeah, but the concept here is that the deeper you go into the neural network, the more abstract the features that you are looking for of the input. Okay. Any questions in this part? Have you already played with the code a little bit? No? I added the 2 convolutions. Yeah, you can add more. You can add more layers. So in this case, I can after here, I can just do like, I'll leave it 32, but I can do like 4 by 2. The trick here is that you use a large stride at the beginning, but as you go deeper, you want to use smaller stride because the images become smaller. And if you take a large jump, you might be ignoring some really important aspects of the input. The convolutions are slower than matrix multiplication. So people try to basically avoid very complex convolutions. And the matrix multiplication is faster, but it takes more computational, like it takes a larger memory on the computer. So there's always this trade-off between slower or less expensive on the memory side. Example, just barely, okay. Yeah, because I added the max pooling. Yeah, so the trick there is that if you remove this, you're not going to get any good performance. So let's just do that. Just remove the max pooling.
I'm seeing your slides and not your code.
Oh,
There you go. Could you point people again to that thing you were talking about with the max?
Yeah, so I said here, I already have, okay, let me go all the way here. So some people saying they're just using the sample code and getting just 50 or something like that, right?
That's correct.
Yeah, so let me try here. Yeah. It's getting slower, so I guess a lot of people are training now. So there's some heavy load on the server now. Yeah. So this is one other aspect of the deep learning network. The weights are initialized randomly, okay? And sometimes you get lucky by getting a good initialization that performs good, like very well. So usually when you are evaluating a machine learning algorithm, you want to have multiple runs, and then you average, because it's not very highly likely, but the smaller the neural network, the more effect of randomness you get. So it means that sometimes you can get a lucky shot that's sometimes just initially you get like 80% accuracy. So in this case, the model is not it's not that large compared to other machine learning models. So you might start in some good neighborhood. Yeah, so some people might get 90 from the beginning, others maybe later. Okay, so with this, I'm going to move to the unsupervised learning part. Okay. So the unsupervised learning part, it's not unsupervised in a way that you don't get the labels, okay? But we're still learning a mapping. And the mapping here, it's not mapping the features to the labels, but it's mapping to some code or some lower dimensional representation that satisfies some constraint, okay? So in this case, if the code that we are trying to learn is discrete, finite, you can talk about clustering or sparse coding. If it's continuous, you might be talking about dimensionality reduction or some generative models. But in all these methods of unsupervised learning, the difference is the properties of the space or the representation that you are trying to learn, and the algorithm that you want to achieve that. Okay. And I'm going to use a very specific example it's not classical in a sense that it's not as old as the clustering algorithms or the sparse coding, but it's very popular in recent applications. And it's a way of using neural network to reduce the dimensions and at the same time have some generative aspect of the data. So in this case, I'm going to move to the unsupervised learning notebook. It's very similar to what I've seen before when it comes to the code part. I'm going to use what we call the MNIST data. So it's basically handwritten digits. I can do plot, mshow, or matchshow. And I can take like the first example. Yeah, this is 5, trust me. Yeah, so then you have 0. And the goal here, these are 28 by 28. So that's like 784 features. And the goal of the autoencoder is to compress the input into a lower dimensional output in a way that the lower dimensional output still contains enough information to build back the original input. So it's kind of a just compression, okay? So we're using a neural network that will map 784 pixels or features to like 4, 10, it's up to you to choose. And based on those 4 features that we have mapped to, we are using another neural network. So that's going to be the decoder that will try to build back the original input from that compressed code. Okay. They don't have to be symmetric or similar in size. There's no constraint. The only constraint is that the output of the encoder should have the same dimensions as the input of the decoder and vice versa. So the output of the decoder should be the same dimension as the input of the encoder. So you can add another arrow here, so it's kind of a cycle. Okay. So the same thing here, I'm creating a sequential model. The difference here is that I'm not using convolutions. And the way I do that is I'm flattening the image. So the image is 28 by 28. So I'm just creating one-dimensional vector. So it's going to be 28 square. That's 784. Okay. And these are stack of matrix multiplications followed by a leaky ReLU, which is a special case. It's more like a general case of one of the ReLU activations. And latent dimension is the dimension of the code. And that's something that I choose. Okay. The decoder is much simpler. Just 3 matrix multiplication. One thing to notice here is I'm using activation. Anyone knows why? I'm using the sigmoid activation for the decoder. So I'm going back. This is where I'm loading the images. The images are 20, like just grayscale in this case. There's no RGB, and the values are between 0 to 20 to 55. So what happened here is that I'm scaling the pixel values to the region, the interval 0, 1. Okay. So what happens here with the sigmoid and the decoder, I'm saying that the decoded code should also be in 0, 1. And the sigmoid activation I showed before, it does exactly that. So no matter what the input is, the output is always going to be between 0 and 1. So here we're already kind of helping the model learn something useful. And in this case, I'm using the latent dimension of 2. It means that I'm mapping all the pixels to 2 dimensions. The optimizer is Adam. When I do Adam, the string, instead of the Adam I used here, it means I'm using the default parameters. So in this case, the default parameter is going to be 10 to minus 3 for the learning rate. So usually when you do this, it means that you are just using the default parameters for the optimizer. On the other hand, the loss here is no longer the cross entropy, it's just the mean squared error. So I'm treating the image just as any vector in some Euclidean space, and I'm computing the distance. It's not really a good distance, right? Because if I have a digit 1 and I shift it, let's try, probably find some 2 examples. Okay, let me see. Yeah, so the Euclidean distance, you're just comparing the images pixel-wise. So when the pixel is 0, the distance is 0. When the pixel is 1, the distance is 0, and vice versa. So imagine here that the one guy here matches the left bottom edge of the 0 character. Then you might actually get one that is close to 0, than having, for example, a 0 that is all the way to the bottom left. So the pixel-wise comparisons using the mean squared error is not a really good distance for images, because you're just comparing pixel-wise the images pixel-wise. So if you have a one digit that is a shifted version of the other, you might get a maximal distance, even though it's the same digit. But in this case, it does fairly well. So I'm going to do the same thing. We have no labels. It means that I'm just taking the input, and I want to make sure that the decoded input is very close to the original data. Oops, I haven't defined it. Okay, it's faster. I guess people are not training now. These are examples I've chosen. They are not random because I know the order of the images in the original data. So I just chosen them to make sure that I get different digits. I'm not just showing 5s everywhere. So this is the original input, and this is the reconstructed one. So it's not doing fairly well. It's not doing that well on this example. On the 1 digit, it's constructing it very close. The 8-3 is not bad, but the 8 is not that good. But let me see how well I do here. Maybe I get some good shot with the initialization this time. Okay. Yeah, slightly better, but not too different. And this is the aspect that I talked about where I call the generative aspect. So don't forget here that I'm mapping the input. I'm mapping my original data to latent dimension, okay? And I have chosen my latent dimension to be 2. Now, since I'm just in a 2-dimensional space here, so the coding space, just 2-dimensional space, I can choose some random samples and decode them. And hopefully I get some new digits that I haven't seen before. This is basically the trick. So imagine here, I map all my data to the space here, and then I choose some data, some point that's very close to the 3s, but not exactly any one of them. And then I decode it, then I get a new digit that I haven't seen before. And this is the generative aspect of the autoencoders. So in this case, I have chosen the coordinates -3, 2, and I want to decode it and see what I get. Yeah, I get almost 3. Let me try -1. Yeah, very close to 5. But very not exactly. And if you have seen like all these AI generated images, the concept is kind of the same. They do it in a more complex way to make sure that you reconstruct something that has high quality and that makes sense, not something that has like 100 fingers. But the idea here is you're still using some large data set that you are encoding in some space. In that case, it will be a very high dimensional one. It's not going to be 2, it's not going to be 4, probably around 2,000 or 3,000 dimensions. And once you figure out how to get, just choose new points in that encoding space, you can decode them, and then you can get new images that you haven't seen before. In this case, it's very simple. I'm just trying to guess -1, -2. Practically, you assume that the encoding is following some distribution. And if you do that, then you are not just choosing randomly. I mean, you're just choosing arbitrarily like samples. You're saying, okay, I'm assuming the encoding is some Gaussian distribution. And if I want to generate new samples, I'm just going to take new samples from that Gaussian distribution. All right. Now you can also do some more tricks, but I will leave this part for you to work with. But I'm just going to show you an example. Let me change the dimension from 2 to like 10. Okay. I'm just making a much simpler model. So why this unsupervised learning is important in machine learning? Because it's easy to do. You don't require labels, because sometimes labels are quite expensive to get. Like imagine some language that's rarely spoken in the world, and you want to do some supervised learning on it. If you have speech that has high dimension, it's expensive to train a model with very few labels. So one thing you can do is actually use like something that we have just this way. you can use an autoencoder to reduce the dimension. So you can have a speech that has like 10,000 features, and then you can use an autoencoder to map it like to 64 or 100 in a way that those 100 features are going to be enough to reconstruct the original speech. In that way, then you can take that code and use it as features for the supervised learning part. And this is very commonly used. I mean, it's basically used all the time in all machine learning models now, especially when the input is high dimensional. So here I did like 10 dimensions. I'm getting slightly better because 10 features, 10 dimensions in the code is going to give me more information. Yeah, this is not going to work now, but let me just try something that's 10, like 3, 2, -1, -2, -4. Okay, I have now 7. Let me add another. Nah, it's not giving anything. So yeah, once the dimension increases, it becomes very difficult to generate. Basically what's happening here, I'm taking a point that is in some empty regions of the code space. Okay, that's a very common thing. Once you increase the dimension, it becomes exponentially difficult to explore the space. But I can use those 10 dimensions to do other tasks. For example, I can cluster the data. So I'm using 2000. So the original data has like 50,000 samples. I'm just going to use 2,000 of them just to do a fast demonstration. And here I'm using TSNE. TSNE is an unsupervised learning algorithm that does dimensionality reduction. Okay. So one way you can just Google scikit-learn. I'm showing you how to catch the fish. Okay. So just scikit-learn clustering. And you have all these machine learning algorithms that you can use for clustering. All of them here. You can even go to any of these. They are explained, what's the mathematics behind it. And you can actually just go there. For example, go to k-means, one of the oldest algorithms. Sorry. Just going to k-means. And there you go. So this is the definition of the function, the different number of parameters, but you're always usually give an example of how to use it. Okay. And they usually have all the same signature. It means that you define the model and then you do the fitting using the data, and then you do the prediction. Usually all the algorithms in scikit-learn have the same structure. Define the model, do the fitting, and do the prediction. Yeah, it's a machine learning model. It's an unsupervised one. Machine learning is not something magical, it's just statistics with more powerful computers. Yeah. Okay, so this is the dimensionality reduction of my 10 features input. So embed is not defined. Okay, I'm just gonna fit it here, see what I get. There you go. Yeah. So the color here, I'm using the true labels to color my embed in here. And I haven't used the labels in my algorithm at all. I haven't told it whether this is 1 or 2 or 3. I just use the autoencoder, and then I use TSNE, which is a very simple non-parametric way to reduce the dimension of the input from 10 to 2. And you can already see that it has a very good performance at clustering the different digits. Okay. So imagine you have someone who has never learned what the numbers are, and you just tell them to separate the numbers, separate the images based on similarity, and I would guess probably around 80 to 90% performance matching the true labels. The algorithm does not know what 0 or 1 is. It just knows that these are very similar. That's it. And autoencoder is one of the simplest like encoding deep learning models you can use. With more powerful ones, with more distributions or assumptions, you can get very, like sometimes like 100% accuracy on the MNIST data set without telling it what the real labels are. Okay. Now, I want to go back to my original supervised problem. So I guess the notebook was killed. So I'm just gonna run everything. Hopefully we can have enough time to get you to show you the tricky example. So the original question of one of the questions was, how relevant is the background features of the image? And it actually took me some time to build this tricky data set in a way that I have made deliberately that all the dogs' pictures had some green in them. Okay, thank you. Yeah. So in this data set that I have built, I made sure that the dog pictures, almost all of them, have some greenery in the background. So what happens here is that if I take some images that of dogs that don't have the green background, then we can see that the algorithm actually thinks it's a dog. So the neural network that I trained thinks that the label dog is actually due to the green background, not the features of the animal. So let me see here. Yeah, it's not doing that well. Let me just use something. Okay. Right. So Relu, okay. I have let's see. I'm just gonna wait for that, but that takes me to the last question, or the last part of the machine learning model, the presentation here. We already talked about that. Talked about, okay. So now imagine I want to use this deep learning model to build some robot that feeds my pets. And I have a dog and a cat. So let's say it feeds them twice a day. But apparently it does not do that well when there's not greenery behind. So it just assumes that it's always a dog. So in this case, if the dog eats first in the morning, like say 2 times in the morning, and the cat comes afterwards, it's not going to feed the cat because it's going to take, assuming it's a dog, it's not going to give it some food like later. So this is what the question of fairness, or the problem of the unexpected consequences of using a machine learning model without understanding what actually happens behind it. So let's say here it seems like it's good. Let me load my tricky data. Oops. What is test? I haven't used test.
Ayub, I think we're still on the slides here.
Okay. Yeah, I'm just saying the. Yeah. So here I'm using other samples where the cats have actually a green background and the dogs don't have green background, and it has 0 accuracy. Yeah. So in machine learning model, you always want to pay attention to the data that you are using. And you have very famous applications like in credit, in machine learning models used by banks to do some loan, some credit score prediction, or whether you are a good candidate to take a loan based on some machine learning model. But if the features have some bias in them, you might be unlucky. I created this. So if I move to the fairness part, I created this synthetic data set where, let's say you have a set of students this is like the speed, which is like the number of seconds they're gonna run a certain distance. The swimming's like the distance they're gonna swim in a certain period of time, their GPA, and then their eye color. Okay. And then here is basically the label means they're probably accepted in a certain sports program. So when I do this, I'm using, sorry, there's no such file. Wait, acceptance. Okay, I guess I have to rerun the notebook. Let me just say start. Oh, okay, because I changed the path. Okay. Yeah. So the dataset is equally balanced between accepted or not accepted, and I'm using a decision tree algorithm to just train my model here. And here I'm showing the decision tree or the decision logic. So here it's looking at X3, so this third feature. So in this case, the features start with 0, 0, 1, 2, 3. It's the eye color. So what happens here is that if the eye color is 0, it's always 0. It's never accepted. And the reason is that the eye color is highly correlated with the acceptant label. Okay. So even though if I evaluate my machine learning model, wait, what is the score here? So I'm using the accuracy score. I fit the model. I plot the tree. Let me evaluate this, okay? So the way I evaluate it, I thought I put this somewhere. Yeah, but let me just do is accuracy score, and I do then CLF predict. So the order, whether the prediction is first or not, is not important for accuracy, but it's important for the other models. So drop. Okay. Okay. So in the performance, I'm getting like 70% accuracy. But I'm only getting that because I put everyone with eye color 0, whatever that is, black or red, whatever you prefer. It just giving is like not being accepted. So if I'm just evaluating the model based on the performance, if 70% is enough for me, I'm not looking at the consequences of actually excluding students that even might have better speed, swimming, or GPA. But because my machine learning model actually based this decision almost uniquely at the first level on the eye color, I'm discriminating against the 0 eye color. Okay. You might think then, well, just drop the eye color feature. What do you think? We have 4 minutes. How would you use this learning environment? No guesses? Okay. So I'm going to do the same thing here. I'm just gonna guess in here. I'm gonna remove the eye color. And let's see what we get. Dropping the accepted. This is the fairness notebook. How would you use this learning environment? Okay, so I'm dropping here the eye color, and I'm gonna see what's happening here. So I don't have the feature, but and then the scoring, I'm still getting the same performance. It means that I'm still actually taking the same decision. Do you want to like any guesses why? Even though I dropped the eye color, the performance of the algorithm is still the same, and it's still making the same decisions of excluding the 0 eye color. Okay, so this will be your homework. And if you actually define, now let's build an algorithm where we drop the accepted. And we're going to try to guess what's the eye color based on these three features. So this artificial or this synthetic data set, if you do the analysis, so you can try to predict the eye color based on the speed, the swimming, and GPA. Can you clarify what that means? Are you asking about what I'm doing now? Okay. So what I'm saying here is that the eye color, or these three features are highly correlated to the eye color in a way that I can guess the eye color with high accuracy based on these three features. So let's say I'm going to use something very simple. I'm just going to use one here. I'm dropping accepted and eye color, and I'm just going to use the target variable. Then is going to be eye color. It's not really rigorous because I'm training and evaluating on the same data, but just give you an idea of the correlation or the high correlation that exists between the features. Yeah, I'm actually predicting eye color better than the accepted threshold. So this feature here has been engineered, but it can also happen. For example, your zip code can be enough information to guess your salary level or vice versa. So, and this is another thing in the ethical part of machine learning, which is that how can I make sure that the features I'm using in my machine learning does not reveal sensitive information about the individuals or whatever the phenomenon is. That's something called privacy in machine learning, and also differential privacy, because sometimes you're training neural networks in a way that you don't want the neural network to catch any information that is sensitive based on the features. I guess I covered everything I had to from these three notebooks. You still have the reinforcement learning notebook that if you want to use, it's more like playing with an environment where you have the agents, the white dot that's trying to reach the red dot. The difference between this and what you would probably see in computer science, where you're trying to find like what's the shortest path, is that here the algorithm does not care about the structure of the environment. The only thing that it cares about is what's the different actions that I can take, and when the game ends, and basically when you reach the final goal, you get a reward. Doesn't matter how many rooms, doesn't matter how large the environment is. So it's more like a generic way of training an algorithm that can reach a certain goal. And it's different from supervised and unsupervised in a way that you just provide the environment to the algorithm, and the algorithm explores the environment itself. So it's basically, it's generating its own labels based on experience. And it's a bit mathematical, didn't get time to simplify it in a way. But if you just run the notebook, you can get a demonstration of what's happening. There's this video at the end, so it shows you how things are happening when you choose a uniform random. So you just blindly exploring the environment. And the best one, which means that the one that you learn based on from the algorithm. Okay. Any questions? I'm aware this can be kind of overwhelming for people who haven't seen this before, but I guess I gave all the ingredients that you need. How to explore the Keras library, the different, this is just an example how to do a simple neural network, and also how to use scikit-learn, like unsupervised learning, but the supervised one is the same, you're just providing new labels. And these two libraries are very well documented. Like K-means is everything is explained here. They are also given references and everything. And the best way for machine learning is just to run the code and see what's happening, then go back to the equations. Otherwise, just starting from the theory can be confusing to a lot of people. Yeah, with that, I'm ending my presentation. Any questions? I'm here. Otherwise, thank you for your time.
Awesome. Ayub, can we give it up for our presenter, Ayub? Thank you so much. Great job. Ty wants to remind people to shut down your virtual machine before you leave. So please be sure to do that and give Ayub some love in the chat or with emojis or however you prefer to do that. We're running up on time. I wanted to just turn it over to Virginia quick. Do you want to make any announcements or say anything about next week or the trainings before we dismiss people for the day?
Sure. We'll be sending out an email with information. There will be a link to a web page where you'll find a ton of information. So hopefully that will answer any questions that you will need for the hackathon. And so, yep, looking forward to seeing you all. And thank you for being here.
Awesome, Virginia. Give it up for all of our presenters. Again, Elsa, Eric, Ty, Ayub, Sabelli, probably forgetting some folks. Great job, everyone. Thanks again for everybody's help. Great job, team. Thank you, Rachel and Virginia, for keeping us on track.
Everybody do some typing calisthenics. We got a big hackathon coming up next week.
Party people. Yes. We look forward to seeing you next week, everyone. Don't forget to stretch, get lots of rest, come ready to ask questions and participate, and feel free to reach out to us if you need anything before then.